Hello, everyone. Welcome to the Fundamentals of Analog Electronic Technology class. We have already studied the basic principles and analytical methods of field effect transistors FETs and bipolar junction transistors BJTs. In this chapter, we will discuss integrated circuits in which various types of transistors and other components are integrated onto a single silicon substrate to realize specific functions. The main topics include DC biasing techniques, differential amplification, and voltage transfer characteristics. Now, let's begin our study of the content in this chapter. In our study of field effect transistors FETs and bipolar junction transistors BJTs, the static operating point is generally biased using a resistive voltage divider. However, in integrated circuits, fabricating a three-terminal active device occupies less area than a resistor and is also more economical. Therefore, in this chapter, we will use FETs or BJTs to provide a constant current DC bias for amplifier circuits. In this lesson, we will study DC biasing in integrated circuits, namely current source circuits. There are two main knowledge points: FET current source circuits, BJT current source circuits. Additionally, we will cover the MOSFET mirror current source. First, let's analyze the first type, the FET current source circuit. As shown in the figure, T sub 1 and T sub 2 are two N-channel enhancement type MOSFETs. The two transistors have identical process parameters and characteristics. As long as the condition V sub GS greater than V sub Tn is satisfied, then in transistor T sub 1, V sub DS1 greater than V sub GS minus V sub Tn will also hold. According to the content from previous chapters, T sub 1 must be operating in the saturation region. Since T sub 1 and T sub 2 have identical characteristics, we have V sub GS2 equals V sub GS1 equals V sub GS. When the drain of T sub 2 is connected to a load to form a loop, as long as V sub DS2 greater than V sub GS minus V sub Tn is satisfied, T sub 2 will also be operating in the saturation region, and I sub O equals I sub D2 equals I sub R EF equals V sub DD plus V sub SS minus V sub GS divided by R. Furthermore, because I sub R EF equals I sub D1 equals K sub N times V sub SS minus V sub Tn to the power of 2, we can determine the current value. The current I sub O is independent of RD. It can be seen that when the value of R sub D changes within a certain range, with V sub DS2 greater than V sub GS minus V sub Tn, the current I sub O will remain unchanged, reflecting the constant current characteristic of I sub O. When the devices have different width to length ratios, I sub O divided by I sub R EF equals I sub D2 divided by sub D1 equals W over L sub 2 divided by W over L sub 1 equals M, where M is called the current transfer ratio. The current characteristic of I sub O is as shown in the figure: V sub DS2 greater than V sub GS minus V sub Tn, and V sub DS2 less than V sub BR. Breakdown voltage I sub O remains essentially constant, and the actual characteristic agrees with the theoretical value. We regard I sub O as the mirror of I sub REF. And since the value of I sub O remains unchanged, this circuit is called a mirror current source. In the figure, R sub O is the drain source resistance of T sub 2. Its reciprocal corresponds to the slope of I sub O. the larger sub O is. The smaller the change in output current I sub O caused by a change in output voltage V sub O, that is, the smaller the slope of the output characteristic, and the better the constant current characteristic of the circuit. To this end, we replace R with T sub 3, as shown in the figure. T sub 1 through T sub 3 have identical characteristics, because I sub D1 equals I sub D3 equals I sub R EF equals K sub N times V sub GS minus V sub Tn to the power of 2. We have V sub GS3 equals V sub GS equals V sub DD plus V sub SS divided by 2. As long as V sub DD plus V sub SS greater than 2V sub Tn, T sub 1 through T sub 3 can operate in the saturation region, and the output current is I sub D2 equals K sub N times V sub GS minus V sub Tn to the power of 2. Additionally, we will cover the BJT mirror current source, as shown in the figure. Its circuit structure is similar to that of the FET mirror current source in the previous section. However, there are two important differences. 1. The base current of a BJT is non-zero. I sub E is not equal to 0. 2. The current transfer ratio M the current source is different. The current transfer ratio of a BJT is determined by the relative emitter areas of T sub 1 and T sub 2. That is, beta sub 1 equals beta sub 2, I sub CO1 equals I sub CO2, lambda sub 1 equals lambda sub 2. When T sub 1 and T sub 2 have identical parameters, we have V sub B2 equals V sub E1, I sub E2 equals I sub E1. When the transistor's beta is large, the base current IB can be neglected, and the collector current I sub C2 of T sub 2 is approximately equal to the reference current I sub REF. That is, I sub C2 equals I sub C1 is approximately equal to I sub REF equals V sub CC minus V sub B divided by R is approximately equal to V sub CC divided by R. When RC changes within a certain range, the current I sub C2 will remain unchanged, reflecting the constant current characteristic of I sub C2. The dynamic resistance of a BJT mirror current source is generally above several hundred kiloohms. Everyone, in this lesson we have studied two types of current source circuits, the FET current source and the BJT current source, and understood that current source circuits provide a stable DC bias for integrated circuits. After class, you should review material and become proficient in these two mirror current source circuits. That concludes our content for today. See you in the next class.